Whilst Berwin debates whether or not to build another 15 minutes or not, let's just start anyway. So, thank you for coming to the Maths and Stats Colloquium. It's my pleasure to introduce Kathy Luge, who's visiting us from the Technical University of Ilmenau for 3 weeks. This is halfway through the 3-week visit. And so Kathy's going to be talking about some work that her group has been doing around reservoir computers, which is kind of interesting to us to parallel some stuff that some of our group have been doing on the same thing, albeit perhaps a bit more theoretically, except perhaps Brady. He's actually solved all of industry's maintenance problems with reservoir computers.
Oh, I wish.
So anyway, I'll give the time to Kathy to talk about her work.
Thank you very much, Michael, for the introduction, and thank you for hosting me this 3 weeks. I'm enjoying my time so far here in Perth. And what I'm going to talk about when I decided which side, I think I will talk to this side here. What I'm going to talk about today is reservoir computing, but not with a normal, typical network approach, but with dynamical systems. And that's why the plan is first to introduce a bit which systems we use, will be photonic systems for these reservoir computing, and then go into how we apply that and what we use that for. Since I moved to Ilmenau 4 years ago now, I learned that putting a map always helps because no one knows where Ilmenau is. So before I've been in Berlin, TU Berlin, and now I'm at TU Ilmenau, which is right in the middle of Germany. So if you forget where it is, you just balance Germany and you find it right there. It's in the middle of the woods, a nice small university with a technical focus. And so the plan for today is, as I said, first, we don't do reservoir computing. We look a bit at dynamical systems, at lasers with feedback, just to know what we use. Then I will introduce this time-multiplexed reservoir computing. And at last, let's see how far we come in the time given. Just stop me when I take too long. I will talk about how we tune the performance when we have these kind of dynamical systems. So let me start with a video that I stole or was given by John Bueno. I was in the PhD examiner panel, and he looked at a laser that is experimental data here, a laser with a mirror behind. And the laser becomes unstable, shows chaotic dynamics. So what we simulate here is then the time dependence of the intensity. And if we plot that here in this way that always one tau is one color-coded line, and we look at it, then you see there is some structure, but it looks more or less chaotic. So a laser, that's what you should learn from that. A laser with a delay can show very complex dynamics, and we want to use this high dimensionality, this high complexity for the reservoir computing later on. If you like to look at it in a different way, if this is too confusing, then the normal power spectra is also a way to look at it. That's the power spectral density over frequency, and you see it's a very broad spectrum that this laser can emit. And of course, it's not doing that all the time, but only for certain parameters. And that is a scan here. That's what we do when we analyze these dynamical systems. We write down first the governing equation. That's a normal differential equation with a delay term, which makes it then a delay differential equation. The most important thing is the electric field squared is the intensity, and that is changing by the gain term. That is here quantum dot laser with a complex gain, which is not that important, but it's the gain, so it's amplified proportional to the field. We have a loss term, and then there is the feedback term from the light that comes back from the past, right? That is the equation. And then we take these two feedback parameters, the feedback strength and the feedback phase. So it can have some phase shift when it comes back from the mirror. That is this phase. And in this plane, we then characterize the dynamics. And what you've just seen, this chaotic stuff, that's more or less in the red region here. That's where we have this output with a lot of maxima, and that is the color code here, the number of maxima we find in the time series. Then it's red. And we see there's some structure in the phase space. Red, as I said, is the complex one. Then we have periodic oscillations with two maxima. That would be the darker red. If there's only one distinct maximum, then it is the light yellow, and the blue one is constant wave emission. So there it's stable. That's what telecommunication people like. And for one line scan across this parameter plane, so phase of pi would be destructive feedback, then we can also look a bit more detail at the maxima, and we see here it is constant wave emission at this intensity. Then I don't know whether you are into bifurcations, but this would be a Hopf bifurcation where one eigenvalue of the Jacobian crosses the zero only for the real part, and the imaginary part is non-zero. We have oscillations. And then the blue and the red here are up and down sweeps, depending on how we tune our parameters, just to show you that these lasers with feedback can have two different dynamics for the same parameters, depending on where you came from. So you have this multi-stability in these dynamics too. And these regions here where it's stable, they are different external cavity modes. From the physicists, I always explain them that it's a standing wave with a different number of maxima inside the resonator. So from here to here, there's always one more maximum inside. And they exist and become more and more depending on the amount of delay. So if we now move our laser further away, the picture stays similar, but these external cavity modes become more and more. That can be understood. Has been analytically also described and solved. But for us to know is when we later use that for the reservoir computing, when we just tune the delay, also our dynamics will change and will become more complex, more multi-stable, and we just have to keep an eye on that. So we know dynamics can be characterized from this laser, and now I want to use it for the reservoir computing, so I need to get some data in. And the question is, what are the possibilities? So this is the setup. This will be our network. And the data, so now if we write our governing equations again, this is the electric field with the losses, and I could get data in by adding additional optical injection with a certain phase, and the phase would then be my data that I want to analyze. Or I could also just play around with the driving current of this laser, perturb it in a different way. That could also be the data that I inject. So I have different possibilities here to get the data in, but what you are asking yourself maybe is, where is the network, right? When you're coming from reservoir computing, usually there is a network. So we have to now think about, why can we look at this as a network? Okay, so we already managed the first part. We know laser is complex. We have to take care of the parameters. And now we use that for this time multiplexed reservoir computing. And time multiplexed means, if you're coming from ChatGPT, then you know deep neural networks, right? You have these layers, and they are all trained with millions, billions of parameters, and these backpropagation algorithms are explored there to get all these lines, all these yellowish connections with their correct weights, which is a tedious task. So training these models takes months, and then they have a mapping between input and output. Reservoir computing is the idea to get away without training. You still get a mapping between input and output, but you only train these linear readout connections at the end. So you basically hope that the network that you have does the nonlinear transformation that you need. You pay for it usually by putting in larger networks, because then you have a higher possibility to get the transformations that you need in your network. And now we come and don't do this spatial network, but we put the laser in here. And this is the spatial thing again. And now we transform that to a time multiplexed network. So what we had with the spatial thing is we had to get the data into the network. We do that by playing around with the current of the laser or the phase, as you've seen, and put that in as a function of time. So each level here is one data point. We hold it constant for a while, put it in. Then the system does something. This will be our laser. It reacts. We record the intensity, if it's a laser, as a function of time, and we read out. And that is then the same as the readout in the spatial. Yeah, so everything that is in space before, in the normal echostate networks that you know, is now in time. So for one data point, we read out, let's say, 10 times. That would be our 10 virtual nodes. If I visualize that in such a time series plot, that would be again the input, boring input 0, 1, 0, 1, right? That would be the input. That would be what my laser is doing. If it's not operated in the chaotic regime, it would just exponentially react, and we read out. That, however, is then every response is somehow predictable one from to the next, from one point to the next, which is in the spatial multiplexed case like you injecting the same input data to all the nodes, which you don't do because there you have the random connections, input connections, and we do that too in this time multiplexed case. So we multiply a mask, just a funnily shaped section of time series, we multiply that on top of our constant input. That is the random input connections. Then we get a response that looks a bit more interesting, which is from the mapping perspective just more linearly independent. So what this node does and what the other node does is not that easily predictable. So we get a higher nonlinear, higher dimensional mapping. And the number of times we read out in one of these intervals is the size of our network. Yeah? This is the number of virtual nodes we have, the size of the network. And then the rest of the story is the same as if you have heard about reservoir computing, the same as before. You just do this minimization, a linear regression, where you minimize the distance between the target, what you want, and the output, what you have. And the output is the state matrix, which contains all these data points. One violet line is one row, the next is the next row, so you get your matrix filled. You need the output connections. They have to be trained, but that does this minimization for you because we have an analytic solution for this minimization, right? I mean, we have that for 200 years already. Gauss and Legendre told us how to do that. So we need the state matrix. If we do it with the regularization parameter, we add this lambda times the unity matrix, and this is our target, what we want to have. So whatever task we have, if this is the target, this is what we measured, then we have the weights, and we can operate our laser system as a reservoir computer. And then, of course, we need to know, is it working or not? So we need some kind of measure to determine if we did good or not. And that will be, in my case, this normalized root mean square error, which is just the distance between target and output. So what I want and what I have, normalized to the variance of the target. Then we have basically everything together to operate our laser as a reservoir computer. You would probably ask, what is this thing supposed to do? So I haven't talked about the task yet. And this is the last introduction that I need. So what is the task? And these time multiplex reservoir computers are nicely suited for time series prediction because they evolve as a dynamical system on its own anyway. So to train them to predict a time evolution is a good fit to use it for this kind of task. So that's what we use here. And we choose some toy model tasks that other people also chose that we are able to compare the results. So it will be this Lorentz task. You probably all know, coming from some atmospheric description. And it can show this chaotic behavior for certain parameters. That is what we choose. And then the tasks can be, of course, designed differently. We could input the x variable in our laser, and then our target would be the next time step of this x variable. We also could put in x and try to predict Z. We could put in all three, predict two. So there are a lot of different tasks you get out of this system. What we usually do is this X to X, but yeah, that can be chosen. The discretization step here, this DT also gives you different tasks. So if I put in these X of t, I already have to choose where I sample my points, right? I have my evolution of my Lorentz system, and then what is my task? I have to sample some points, and how I choose them is already a choice that I do to get my task ready. Yeah? So in the literature, it's usually 0.1, but some people take smaller or larger step sizes, which are different tasks and need different things. We'll see later on. And the other one we will use is the Mackey glass system, a delay system on its own, which also shows a chaotic evolution along a attractor, and this is what we try to predict. All right, so here are now some results for this laser. It's a quantum dot laser, but that's the physics part, not that important. It's a semiconductor laser. I told you about this feedback phase and feedback strength part, where we have the stable operation, then the Hopf bifurcation, the complex. Oh, the color code is changed. Sorry for that. Different student, different color code. But red now means only 2 maxima, and yellow is the complex. Just realize now that this is switched. And this funny line here, that is due to the initial conditions that were chosen when the student did the scans for the dynamics, because you've seen this multi-stability, and depending on where you come from, you land on either the one solution that it's like a folded piece of paper here, this solution lies beneath the other one, and depending on where you come from. So this is just an artificial line where the attractor distance is, the attractor personnel is different. But these initial conditions have also been chosen for testing this performance. So here, now this is the reservoir computing performance. That is this normalized root mean square error. Dark means good performance. Bright means not that good performance. And what you see for, this case was the Lorentz X to X task. For not that high feedback strengths, we got the best performance. Behind this Hopf bifurcation, it's not working at all. So as soon as the laser starts to behave funny, like these chaotic dynamics that you saw in the beginning, you cannot train it anymore, which is known as this echo state property. When your laser itself is not predictive anymore, it reacts differently to different inputs, of course, then you cannot train it to tell you something consistent. So you have to be outside this complex region. And then for this task, it seems to work nicely for small feedback strengths.
Sorry, Kathy, the quantum dot laser is behaving chaotically, or the target system? The actual oh no, sorry, this is Lorentz, right?
It is Lorentz. The target is the Lorentz, and that is chaotic. The quantum dot laser, that is stable here in all these regions where it's blue. But what we did now is we used different quantum dot lasers because we wanted to understand, does the dynamics of this quantum dot laser change the way these performance measures turn out? And this is the row here. So from left to right are different lasers. Think of putting quantum dots with different size. From a dynamical standpoint or from a mathematical standpoint, it is the response time that is changing. So in this case here, that is the turn-on dynamics, the laser shows very strong relaxation oscillations, so it has a complex eigenvalue when you look at the Jacobian. Here in the middle, it is very strongly damped, and on the right, it is again showing these relaxation oscillations. We tuned that by changing the scattering rates in this laser. The dynamics is plotted in the first row. So when there are these huge relaxation oscillations, it is more easy to destabilize the laser with the feedback, and that's why we see these yellow regions earlier. Here it's more stable because the eigenvalue here, the one that is responsible for the damping, is larger. And below, we plot the computing error. And we see a nice correspondence. So it's for every laser, we always have the bad performance behind the bifurcation, but the nice performance for these small feedback strengths. And for the echostat networks, you usually learn you should be at the edge of chaos or something, which is in the spatial case before it becomes unstable. But here in this case, this is actually not the case, because edge of chaos, edge of bifurcation, if we interpret it this way, it should be here. But for this Lorentz task, the good operation is just before for these small feedback strengths. But and that was specific for this laser. If we look at a different task, the Mackie glass task, which needs much more memory to predict, because you have this delay equation and you know the next step, you need to know more history of your task, then all of a sudden, so the first row is the same because the same different lasers. But the second row is now the Mackie glass task prediction performance. And here, that looks much more in agreement with this edge of chaos thing. It works very nicely, very close to the Hopf bifurcation. So when the Hopf bifurcation change, also this best performance points change. And that tells us again that the task that you look at is also important for the properties of the reservoir that you need. This Lorentz X to X task is not that hard in terms of memory. So you don't need these long transients that you have close to the bifurcation. Right? Close to the bifurcation, the system is nearly undamped, so it has very long transient responses, which gives you a lot of memory. So here it is working nicely close to the Hopf bifurcation. Yeah, this plot here was more interesting for the number of degrees of freedom we have in the quantum dot laser. That was surprising. So if I go back here, that is performance plotted over the scattering rate, so over these different lasers. From left to right, different lasers, overdamped regime, synchronized regime. And we guessed in the beginning that this middle part, where it's a real quantum dot laser, we have 3 different type of carriers and they scatter and there are a lot of dynamical degrees of freedom. So dynamically, the system is more complex in the middle. While at the edges, I can eliminate 2 equations. So I have basically a 2-dimensional system left on the edges here, while it's 3-dimensional without the delay in the middle. So we were thinking more dimensional system should work better. It obviously doesn't, because the response in the photons, that looks much less complex. So when you think of which system I should take, a complex one, it's always a question, what do I probe? So if I would be able to probe the electrons, that would probably work better in the middle. But since I can only probe the photons, the quantum dots really didn't help. Normal quantum Bell laser would work much better. All right, so then one hyperparameter I didn't talk about yet is this time scale of the node distance. So we have to remember again how we put in our data. It was this sample and hold thing of the task, and then we had the mask, and every mask step is basically one virtual node. And how long we put in one of these virtual nodes is our choice. And what has been known also for this time multiplex system, and what we've also seen, when you plot the performance over these node distance, over the theta, you see an optimum kind of. So you should see somehow a quadratic thingy here with an optimal value where the response of the laser is nicely in check with the time you need to input one of this virtual node. And this little bump, that is the resonance where the delay time and the clock cycle are equal. So this clock cycle here and the delay time of the laser, there it's not working very nicely. So you have to take that one out, and then we have the optimum. And that seems to work for all these different lasers. So here are these scattering rates again. We tuned our quantum dot laser. These solid lines are the eigenvalues of the Jacobian. So we see only two, one in this case in this reddish part, and then they get the decay times are plotted, get smaller, and then gets up again. And the green is this optimal value that we find for all these lasers, and that follows the eigenvalues. So if we know the response time of our system, we have a nice way to find the optimal node distance for a given delay. In our case, the delay was constant. And now I want to show you this plot, which is a bit complicated, but I hope I can talk you through. This is now both time scales that we have in our system varied at the same time. So here is the delay time. So I move my mirror back and forth. And down here is the clock cycle, is this theta value. Maybe shortly back. This clock cycle, how long I take to input one information. That is the other axis. And what you've seen before, this line scan was along this line. So we had this nice optimum. Where it's very dark, we find the optimal theta. And if you wouldn't look at the delay, you would say, okay, I scan, I get the optimal theta, done. But surprisingly, if I change the delay, this optimal theta moves with the delay. So I get this slope that for a small delay time, a clock cycle of, I don't know, 1.5 would be nice, but for a delay of 2, then I need 3.2. For the clock cycle. So also this setup for our mirror determines where, how long I should input one of these data points. And these two graphs here are two different lasers again for these quantum dots. And we see also here these slope changes. So the very overdamped laser has a different slope that moves with the delay than the other laser. And then we try to understand what's going on with this slope. So why is this ratio between tau and t changing with the dynamics of our system? As you see here, that's the slope plotted over these laser timescales again. And the answer lies in the topology. So that is tried to visualize here. I try to visualize here. We don't really have a network, right? We only have one laser. But still, these different points in time interact with each other. So these different points in time are these circles, and these not that bright lines are the interaction due to the transient dynamics of my system. And these darker lines are the interaction due to the delay. So when I'm at a certain point and my past hits me back, then I have a self-coupling of the nodes to each other. While this is this coupling due to the slowliness of my reservoir to react to one of these inputs. If I tune my delay time that it's not resonant anymore, then these arrows here, they hit another neighboring virtual node. So I kind of change the topology every time I change the tau. And I can write that down as an equation. So my delay time is always the clock cycle plus or minus a bit offset, right? It can go plus or minus in the coupling, and that gives me this slope. So the most, so if it's 1 or 2 times the slope here in this diagram tells me whether one of these virtual nodes couples to the next or the previous next clock cycle. And interestingly, that also depends on the task. So now if you have the Mackey-Glass task and the Lorentz task again. Before we saw the Mackey-Glass task liked to be at the bifurcation, at the edge of chaos. And this Mackey-Glass task also likes to have a much higher slope. So for the Mackey-Glass task, the delay should be at least twice as long as the clock cycle. just because it needs more memory. I can also put in more memory with putting in a longer delay, while the Lorentz task, that likes to stay around 1. So with these 2 time scales, the transient dynamics of the laser and the delay, we can tune the coupling topology to our task. So every time I have a different task, I would need to tune something. The quantum dot laser I probably cannot change. It's grown in there. But the delay time I can change, right? And so I can adjust this reservoir to different tasks very easily. And the last thing about this topology that we tried, what if I take the laser out completely? So now, no laser in here, still the delay, but that would be like an optical amplifier that has an instant response. So it's not a dynamical system, but a nonlinear system like you have in these echo-state networks. So just, it's written here, it's these sigmoid functions. If you put in too much power, it's not amplified. If you do a little bit power, it is amplified. And then you couple it back. So it's a very simple map equation where if we think of this coupling topology, and if we are at the resonant case, there are no interactions between adjacent nodes. So we eliminated them. No transient response, no dynamical system. The only coupling we have is now due to the delay. And if we now tune the delay just by 1 node off, then we have a ring, a pure ring without anything else. And then a scan in the feedback delay time looks like that. We always have these resonances when clock cycle and delay time are equal. So there it's not working nicely. But then we have an overall optimum, which is in this case, it was the Lorentz cross prediction, which needs some memory because to predict the Z variable, it needs to do an embedding if it needs to get that out of the X variable. And there obviously a delay around 8 was nice. Yeah, so there is a zoom. So just being next to this resonant case gave good results. Yeah, so that basically hopefully convinced you that we can nicely tune the coupling topology by playing around with the timescales. Although the setup is always the same, a laser with delay or a very, very slow laser like this amplifier with delay, and it can nicely do this time series prediction. And now one last point. Do I have 5 minutes? Should be fast. Is do we have any chances to tune these requirements of the task? As we have seen, the Mackie glass needed memory, the other one not that much. And if we don't want to tune our setup, can we tune that externally? And for that, I want to show you this graph, what we tried to do. So this part I've already talked about. That is what changes when we change the internal feedback delay. That changed the coupling topology, the internal coupling topology. We can use that to optimize our setup. But what if we do this memory tuning before the data even gets into the laser? So these green lines, that was for an optics talk, are supposed to be some fibers. So the data comes in, and this data here takes a bit longer to come in than the other data. Yeah? So just think of the Mackie glass task with the mask feeding in just a bit shifted and added and then gone into our reservoir. That would be input delay. And the same could be thought of at the output. So when the laser is done converting the input to some complex time series, we shift it a bit and we augment the readout, the state matrix, with the delayed one. So our state matrix grows by a factor of 2, and that would be the output delay. And if we look at this output delay case first, so here is this sketch, the state matrix, that is all the intensities. And now we shift that a bit and just write it next to it. The state matrix is a bit larger, we have more features. And here is now the performance map. That is the shift of the first part, and that is the shift of the second part that is added here. And obviously there's a sweet spot. Dark means good, normalized root mean square error, a sweet spot for this given task. I think that was Lorentz x to x. I didn't write it down. But for this task, I can find the optimal shift, which improves my performance, which then is much easier than tuning my laser. I could just take whatever laser I have, with whatever parameters. I augment the memory the way I need it, and I get good performance. And here's a line scan where you see the training and the testing error, and this reddish line is when you don't do this augmentation of the memory. So there is also a nice option to tune the performance of every reservoir computer. You can also do that with an echo state or with a spatially multiplexed, whatever you have. You take your readout, you delay it a bit, and you write it next to your state matrix. And that should improve the results because you give it more memory, and if your task needs more memory, that helps. And that was also experimentally tested. We had two groups. One was doing it with an electro-optical setup in Brussels, in the group of Serge Massar, and the other one with an VCSEL, with an actual laser setup. And this post-processing seems to work very nicely and makes the experimentalists happy because everything we need from them is the normal measured output, and the rest can be done offline. All right, and this is the last slide. Now, just as a comparison, these three things for the optimization, that is the feedback delay is internally tuning the setup, output delay and input delay, and this is without any delay. So what you're supposed to see is here, it's not working that nicely. We have a root mean square error, I don't know which task it was, but 0.06, and that improves by a factor of 6 to the more or less same value, no matter which way of augmenting the memory you choose. So if you have a setup that is not working nicely, it was the Mackie Glass task, it's written there. Not nicely working for the Mackie Glass task because you need memory. You can put the memory on to different positions and get your error much, much lower. Oh, I had another session, but I think I will leave that out. That was tuning with optical injection with nice bifurcation plots, but maybe it's too much for now. And I will stop here with the conclusion that I hope I convinced you that this time multiplex reservoir computing with physical systems is a nice way for hardware implementations, because we don't need to synchronize a lot of lasers or a lot of devices. We just need one. And when we take a bit of care of how we tune our timescales, which we of course should do, then this is performing very nicely because we have the chance to tune the coupling topology with the time scales. And we can add memory if we need some, just by external tuning of the whole system. Oops. Oh. And I want to thank the group, of course. That's the group in Ilmen now, right now. And that was 2 years ago, and Huifang was doing this quantum dot laser simulations. So I put in this older picture. And I want to thank you for your attention.
So, of course, we have time for questions. Okay.
Maybe a less interesting question. What's a quantum dot?
A very interesting question. Well, the word quantum is there because the electrons in these little pyramids that you saw just have 0 degrees of freedom. So you just build a prism for the electrons. So they have a dimension of 20 times 20 nanometers and then 4 nanometers high. And these experimentalists can grow that epitextually. So they put some materials on top of each other that don't really fit. And then these pyramids form. And inside these pyramids, for the electron, there is not much space. So for this electron, it's like a quantum prism. So it has a localized energy level, and that's why quantum. So it's not in a semiconductor in your mouse or something. You have these quantum Bell lasers where you have two-dimensional ways of freedom for your electron. And in a quantum dot, it's basically stays put, which is good for the output emission wavelengths because it is very constant and not moving.
A lot of the results, the optimal result depends on how far back in time the delay is in the reservoir.
Yeah.
And particularly for the case of Lorenz predicting X, where optimal performance was in a non-chaotic regime. So the reservoir is not actually, it's some sort of almost static transformation of your input data, right?
What do you mean with homostatic? I mean,
so it's not doing anything chaotic and interesting. It's just some sort of transformation of the.
Well, it's a transformation, but it's still doing something. It's far from the bifurcation, but still the excursion in phase space is a highly nonlinear response. So you perturb it, and it does this phase space excursion.
So
what you sample.
The optimal delay time, strikes me, this is going to be close to those in optimal embedding window if you do delay reconstruction.
Yes, for the Mackie glass, it is exactly like, yeah, for the Mackie glass, the optimal delay that you find is close to the tau.
Yeah.
But it's not exactly the tau. It's close to it because you still have this interaction of the next neighbors.
The Lorenz is longer? Or?
That was shorter. Shorter, much shorter.
Any other questions?
When you're controlling the spacing between the nodes and then the size of the delay, things like you're sort of playing around with the size of the reservoir as well, right? Even in a sense like with echocentrics, but just the number of nodes is so important, right? How does that work for something like this, these delay systems where there's so much correlation between nodes?
Yeah, I mean, that's always the difficult part because you tune both at the same time. So these graphs that I showed you where I tuned the theta, I left the number of nodes constant. But you can, of course, also sample more often and make your theta shorter this way.
Sampling sort of similar information?
If you come too close to each other, then the information you get is linearly dependent. So then you can sample twice as much. It's not helping you anymore. So that's what you definitely see when you just increase the number of sampling points. If you do more points, but also increase the window, so that each point still has the same theta, but then you just need to feed it in longer to get all the nodes in. There's also a saturation that you see at a certain number of nodes because they don't interact that much. If the ring gets so large, then you just have this next neighbor coupling, which is only a small part of the ring, and then it's also not helping to put more.
Is that why the performance, did the performance decrease when you were sampling more and more, getting more virtual nodes, just because you were sort of overfitting and there was too much movement dependence? There was like a graph, I think.
I didn't do more nodes. It was always 30 nodes. Or which graph do you? Wait, I didn't show those.
I guess the theta was changing.
Yeah, the theta was. You mean this this one here? No, that was the delay. This one?
No, I think it was. Yeah, there was a performance graph. I thought it was against theta. So I thought that meant like the number.
Oh, you mean this one here? This one?
Yeah.
There, the number of nodes was constant. Just to take that out, because if you also make more nodes, then you have a higher dimension of your state matrix, and then you mix all the effects. So here, the number of nodes has been not changed, and instead, when changing theta, this t just grows.
Oh, so you're just flattening your input forward.
Yeah, but that comes after, right? I'm sampling my Lorentz. That is done, and now I hold it for longer to feed it in.
Oh, okay.
Same number of nodes, but maybe less different from one another.
Okay.
Yeah, and if you do more nodes, of course, you can gain some stuff when you still get some independent information, some more information. So if your task is very demanding, then having more nodes is, of course, a good thing. Yeah.
Just in terms of the magic glass model,
Yeah, that is a good question.
How much did you tell the cat back? Because, I mean, you already need a reservoir, even for the Lorentz one. You need a reservoir data to feed your model, to train it.
Yeah, but that is, I would not call that memory. So the number of training data points you need, that is one thing, but that is not the memory that your task needs. So you feed in your certain training data, but the question is how many points of your training data your reservoir needs to remember to predict the next step. So if you now feed it in unseen data, let's say 3 data points of the Lorentz or Mackey glass, and then you ask it what is the next. And the question is what is the minimum number of data points it needs to do the next prediction. And for Lorentz, 2, 3, 4 data points, it now depends of course on the scale, are enough, while for Mackey glass you need more points before it is able to do one prediction.
And this is related to the correlation time delay and Mackey glass delay.
Yeah, yeah.
Next year, how the delay time and that every
Yes. Which then, of course, also depends on the sampling, right? If you sampled your Mackey glass with a larger distance, then you just need a delay of 2 points, which is then still the delay time that you factor, yeah.
But it doesn't affect that much in terms of the training data.
No. The training data here, of course, have to be long enough. Well, not too short and not too long, so something in the middle. Yeah, but that's usually chosen by looking at training and testing error. So as soon as training and testing error somehow converge, that's the training length that we choose. Because when training and testing error start to diverge, then you have this overfitting problem that it's just doing the training good but not the testing. So you can find that out, how much training data you need.
Find the length of the optimal length for the training data just experimental.
Yeah.
Okay, any last questions? You've had one.
Well, hardly counted.
So, if it was like, just you can sort of map the time multiplex to like a loop
Yeah.
in the spatial loop, what would be like the intuitive meaning of increasing the spacing in the time multiplex for the same number of nodes in a spatial loop in a set time?
Yeah, what you change is basically the number of next neighbors that couple. So in this picture here, this arrow is stronger when they are closer together because before the next input comes, the laser is not completely recovered and they interact. And if you make them far apart in time, then this link starts to disappear. So if it's very strong, it will still impact the others. So you have a range of next neighbor couplings. And if it is very short, then there is no real interaction. If it's very long, there's no real interaction because it is completely back to its steady state, forgot everything before the next data point comes. And then you are in this map limit where you perturb your system, it stays put at this point.
There's no connections at all.
Yeah. And then you just get the interaction with the delay. If you have then an additional line, you feed the data back in, then it's interacting again.
Okay. Before Tom thinks of any more questions, let's thank Kathy once again. And you're all invited to join us up in the Monadelphous tea room for wine and cheese and whatever the house put on. I hope so. If you don't know where that is, follow someone that looks like they do know where they're going. And Tom can think of more questions on the way.
Happy to answer them later.